session will be Fengshan Liu, who will be talking about isophotal structures of CANDELS star-forming galaxies.
Thanks. Hello, everyone. My name is Fengshan Liu. I come from Shenyang Normal University. In my talk, I will show you the isophotal structure of star-forming galaxies between redshift 0.5 and 1.8 in CANDELS, which was used to trace the buildups of central bulges and the outer stellar halos. This is a recent work of my graduate student Dongfei Jiang, who was supervised by I and Xianzhong Zheng at PMO. As we all know, galaxies in the local universe come in different shapes and size, but primarily consist of two major stellar components, bulge and disk. The fairly large spiral galaxies in the local universe, such as our home galaxies, the Milky Way, usually have extended stellar halos. Stellar halo is also a natural prediction in theoretical model. This slide shows the intrinsic geometry of galaxies, the parallel spheroid, oblate spheroid, and oblate disk. From left to right, the ratio of the maximum rotation velocity to the mean velocity dispersion increased. Okay, it has been known the spheroidal galaxies in the local universe can be classified into disky and boxy in terms of their isophotal shapes. This dichotomy originates from the structure of the stellar orbits that make up the galaxy. Generally, disk feature indicates a considerable rotation, whereas the boxy feature shows random motions dominated. Okay. It has also been shown the isophotal boxy disky parameter A4 is correlated with kinematic parameter, the ratio, the maximum velocity, rotation velocity to the mean velocity dispersion. In addition, the ellipticity of galaxies is also closely correlated with this kinematic parameter. So, analysis by combining ellipticity and A4 would be helpful to diagnose the kinematics of galaxies. Statistically, the central bulge and outer stellar halo are much rounder compared to the disk in the intermediate regions, especially when seen in nearly hadron. On the left is an example in the local universe. It can be seen three stellar components can be resolved in its ellipticity profiles and the surface brightness profile. The red plot is a stack of many nearby disk galaxies by Zheng et al. You can see the arc shape is also clear in ellipticity profiles. So, studying the spatially isophotal properties and their changes with time is helpful to understand these stellar components, how these stellar components formed. This is the basic idea of this work. Oh, okay. Here are the sample selection criteria. The sample used in this work was selected from Gauss and UDS fields in CANDELS. For UVG-defined star-forming galaxies only, redshifts between 0.5 and 1.8, stellar mass between 10 to 9 and 10 to 11 solar mass, and so on. Global data come from the CANDELS team. You can find details in Santini et al. And Van Wille's papers. The spatially resolved data come from our own multi-photometry catalogs. These catalogs are available to all CANDELS members and close collaborators only. If other people are interested in these catalogs, you can email me. The following two slides illustrate our measurement with 3 nearly edge-on galaxies and 3 nearly face-on galaxies. Okay, the top panels are the UVG color diagrams in 3 redshift bins. The bottom panels are the size-mass relations for star-forming galaxies only. In this work, we applied the relative size difference to divide our galaxies into small size and large size. Yes, we found these galaxies have they have different asphotal properties. In the analysis, we followed the germ and Sandisk method to use mice and redshift grid to trace how galaxies evolve along these evolutionary tracks. Okay, now let me show you some main results. This slide shows the ellipticity as a function of a normalized radius for small size galaxies only. Nearly edge-on views and face-on views are shown with red and green symbols respectively. First, let's focus on galaxies at a relatively low mass and high redshift. So you can see these galaxies generally have nearly flat ellipticity profiles in both edge-on and face-on views. The findings indicate that these galaxies might have a single component. Furthermore, in A4 profiles, you can also find quite flat profiles in both edge-on and face-on views. So these findings indicate these galaxies might have extremely slow rotation or no rotation. So, to conclude, these small size galaxies are not disk-like. Okay. Now let's compare it with large size galaxies in the same mice redshift bins. Let's focus on the edge-on views. You can see these galaxies generally have mildly increasing ellipticity profiles, and the intermediate regions are mildly disky. So this results indicates that these galaxies may harbor slowly rotating disk. Okay. So let's see the galaxies at relatively high mass and lower redshifts. You can see the arc shape emerges and become prevalent in ellipticity profiles for both small and large size galaxies, and also in A4 profiles. Okay, so these findings indicate that the centers and outskirts become much rounder and dominated by random motions, and the intermediate regions become more fast rotating. So such a feature can be formed by the buildups of central bulges and outer stellar halos in lockstep with the disk growth in the intermediate region. Okay. Here, I summarize the resolved structure of these galaxies at different bins. You can follow how the structure evolve along these tracks. For example, for the present Milky Way-like galaxies, you can find the Milky Way-like galaxies build up their bulges and outer stellar halos after redshift around 1.4. We also inspected the imagings in nearly hadron. The visually inspection is in agreement with our isophotal analysis. Okay, so now we are more interested in the outer skirts. So we proposed an explanation of the buildup of outer stellar halo. So one reason is the outer skirts are dominated by random motions. A follow-up work also by Dongfei, so who is investigated the stellar populations of the outer skirts with the Wei-Chen-Wang's method. So yeah, so the top panels are UVG color diagrams. Oh, sorry. Yeah, the bottom panels are UVI color diagrams. So Wei-Chen has shown that. So yeah, so along these directions, specific starving rate and absorption and age. So the dust content declines, but the specific starving rate and age are almost consistent. So we extended this analysis to the large areas. So you can see in the inner region, the color gradients are dominated by the dust, but in the outer part, they are dominated by the age. So the outer parts are older than the inner parts. Okay, so yeah, we proposed this explanation with the buildup of outer stellar halo. So as I said, so one reason is the outer skirts are dominated by random motions. Another reason is the outer skirts are older. So these findings are consistent with the prediction in periodic model. Okay, here is a summary. Yeah, no more. Thanks. Sorry, what? Graphite? Not graphite, so just from our own measurement. Yeah.
He asked you how many galaxies you threw away because the smooth fits were not good fits.
So you mean how many galaxies are good fits? What fraction? So more than 50%, I think. So a good fits.
50 or
50%. Yeah.
You have to throw away
15%. Yeah.
50.
50. Yeah. Okay.
Yeah, I showed an image from Corrigan for getting low redshift which is 4638 and electricity profile. If you took some of your lowest redshift star forming galaxies and you just dated them, would they resemble something like
Sorry, so I can't hear clear.
Can you?
Yeah.
So
Sorry.
you showed the Corrigan results at low redshift and some of the different results at low redshift of electricity profiles.
Yeah.
How much do your results at your lowest redshift then connect to those redshift to 0 results?
Yeah. So yeah, in this work, we investigate the results in the intermediate redshift, right? So yes, so it's good a question to compare our results with the results in the local universe, such as Zheng et al.'s results. So yeah, we will check that. Yeah, that is a good suggestion. Yeah. Thank you.